Hello all. Welcome to week two of the deep learning doubt sharing session. Yeah, you can. So this time we covered uh, mostly sigmoid neurons and multi-layer perceptrons in the lectures. So if you have any doubts regarding that or maybe the past week, we can have a discussion or tackling session for that. You can just unmute yourself or you can type your questions in the chat. So the deadline for the first assignment is tomorrow. Hope you are able to solve the problems there. I think both of the deadlines are tomorrow for week one and week two. So were you able to understand the gradient descent algorithm? Uh, so if you have any doubts, you can go over that or how the learning happens.
So in this session, like only doubts will be taken.
Yeah, if you have any doubts, so you can discuss also any other problem that you have. Because the submission for the assignments are not yet done, so we cannot discuss the solutions right now. Otherwise, if you have any doubts regarding the lectures that were uploaded during the last week, so say week two for this one, so we can discuss those questions. So has anyone ever taken the machine learning course, either in NPTEL or somewhere?
Yes, I have completed my internship in artificial intelligence with academia.
Okay, so so is this the first time you're learning about neural networks, or was it covered in that course also?
Actually, major part of Python and the basic of neural network was covered there, and now I'm in college pursuing BE in AI and data science. So actually,
Okay,
the
okay,
thing is that this course and my college is going side by side and same. So that's the reason.
okay. So in the college, you'll also have the opportunity for assignments and coding projects.
Oh
So
yes,
yeah, yeah.
yes.
So which year are you in?
I'm in final year, seventh sem.
Seventh sem. Okay, so you must have done some projects in deep
Yes, I
learning.
have. I have done like object detection all of that using
Okay.
OpenCV.
So you have worked with these fusion libraries like OpenCV or something like that.
Sorry, I didn't get you.
So you must have worked with computer vision libraries, right? OpenCV.
Yes, I
Uh,
have worked with that.
so this course is it's still starting out, but yeah, those things will be covered in the later parts of the course.
Okay. So one doubt I had was that today you will mean we'll do theory and practical both, right? For sigmoid and perceptron.
So we don't. So for this sigmoid, we don't have a practical implementation right now. But when we cover some algorithms like RNNs or CNNs, we'll have some in present some notebooks here. So right now
Okay.
there is not much scope for practical because these are the just theoretical topics. I think
Okay.
the lecture the professor showed some like the implementation of gradient descent. So that is about it.
Okay.
So if anyone has any doubts regarding those, we can discuss this here.
Okay. Cool.
So Aditya, can you speak up? I mean, what sort of help are you looking for?
Uh, are you able to hear?
Yes, yes.
Yeah, so my issue was I don't know where to begin actually.
Okay. So have you taken a machine learning course before this one?
I have taken deep learning course from IIT Madras.
Okay. Uh, so you're from IIT Madras.
No, I'm not.
Acha, acha. So you have taken the deep learning course. So you are again taking this course or what? You're repeating this course?
Yeah.
Okay. So if you complete, what is the problem you're having? Can you explain?
How am I able to access the courses? Where am I supposed to access the course materials and assignments?
So you must have signed in to this Swayam portal, right?
Yeah.
And so if you go to the Swayam portal, you can search for this deep learning course, CS114. And if you register there, you can access the lectures and the assignments there.
Okay. And about the exam, do I need to register for the exam right away or can I do it later?
So I think there is a deadline for registering for this exam. So it should be written in the main page, I guess.
All right. Where am I? Is there is the deadline there on portal itself?
So I am not sure about the deadline. Can you confirm it? Let me check if I can do it. But you can mail the NPTEL team regarding this.
I'm sorry.
I'm not sure about the deadline for registering for this examination course. For this examination. Uh, I think the deadline is August 12th for registering for this exam. So you have to register before that, 12th of August.
All right. Thank you.
So again, does anybody have any problem with deriving the understanding of the gradient descent algorithm? Uh, how you use the Taylor series approximation? How we derive this uh, the direction of gradient and all those things.
Yes, actually, I have a doubt right where the Taylor series came into the picture.
Okay.
So, I mean, I don't know why. I mean, my question is that why do we use Taylor series to derive it further? And that's where I was stuck.
Okay.
I'm not
Okay.
able to move forward further from that.
Okay. Sure. So let
Also expanding on that same question, if you can explain the gradient doesn't a little bit more, that would really help.
yeah. Sure. Sure. Let me share my slide screen. So my screen is visible, right?
Oh,
Okay.
yes.
Uh-huh. So first of all, we look into the Taylor series. So Taylor series expansion says that suppose you have some function, right? Suppose I'm talking about function. So this is your x-axis, say, and you have some function like this. And now I want to know, I want to approximate this function. Say I say that I give you a point, say here, I give you a point, say x1, and I want to know how the function looks like here at this point, and to know how the function looks like at this point. Now at this point, if I draw a line, suppose I say that my function is a line, so I can say that at this exactly this point, my function looks something like this, right? So is that clear?
Oh,
So that
yes.
so that means if I take just a single derivative, the slope of the function, so my function looks like this. Now, if I say I want more information about that function, so now what I'll do take the second derivative at this point. So if I take a so our derivative is a slope, so it will look like a line. So now if I take a second derivative of this slope, so it is actually the Hessian of the matrix. So you must have heard about this term Hessian in the lecture. So if we
Oh,
use that,
yes, sir.
hmm, so if we use that, we can see that function it improves. It looks something like this. Now, if I use a third order derivative, it will again give something like this. Say. So what I mean to say is that if we increase the so given some, so this is some f that you have, and I want to approximately know what this function looks like at x1, but I do not know the form of f. So I can increasingly take the first derivative, the second derivative, third derivative, and so on till, so at some point I will be able to approximate the function f at this point. So Taylor tells us that suppose you have some function f and you are at a point x, and I want to look in the neighborhood of x, say h. So h is something in the neighborhood of x x1. So say this is x, I want to say suppose this is h or this is h. How does the function look like in the neighborhood of x? So I want to derive the function in the neighborhood of x. This is basically the function of x1 plus. So first of all, we took the first derivative, right? So this line was the first derivative. So then we will take the derivative of this function, or I'll say f dash x1 at h times x dash x1, because I am looking at this quantity. So if you look at this quantity, so how does it look like? So yeah, I will use this one. So how does this look like? So this is a line because this is a derivative, or this is a slope, you can say. This is mx plus c. You got this? So this is m, this is x plus c, which is the equation of a line, right? So that means if I take only the first derivative, I can approximate this function as a line, right? Now, if I say that I want to take one more derivative, say I want to take the second degree derivative, which is it's given like this, f double derivative of 2. So here if you look at it, so this is a square, this is a power 1 term, and there is no term. So this looks like a parabola. So if you take two derivatives, we'll get a parabola. So if you take three derivatives, you will get something like this. If you get four, you will take four, you will get something like this. So the more number of powers that you use, the more closely you will be approximate this function f around x. So is this notion clear to you?
Oh, yes, it's clear. So, one last doubt I had, what does exactly Hessian do?
Okay.
I've understood the entire concept of finding the structure in the neighborhood, but what is the role of Hessian?
Mhm. So, okay. So suppose you have this curve, right? And suppose at this point, if I say, what is the gradient of this curve? So the gradient of this curve is something like this. So this is one second. So this is something like dd of, so suppose this is f, ddx of f, right? Now I want to see how this, so this is the curve. This says how does the function changes as we change f. So this is the rate of change of the function as we change f. So this is your first derivative. Now suppose I want to see how does the gradient changes, or how does the derivative changes. So this is our derivative. this is our derivative, this is our derivative. So I want to say that I want to see how this, so this is our derivative. I want to see how does this change, right? So this you can equivalently write it as this. So Hessian actually gives us how curved the function is. You see how curved the function is.
Okay.
So Hessian, if you talk about a multi-dimensional, say we have a 2D data, suppose say we are plotting on the 3D scale, and this is your x1, this is x2, and we have some bowl shaped here. So Hessian will basically say how much curved this thing is. So if our Hessian values is, say, suppose we get a matrix, say 5, 5. So what this means is that if we suppose we look at this Hessian from above, right? So we are looking it from above. So we'll see some circular things. Can you visualize this? If you look at the Hessian from above,
Yes,
look at,
yes.
ah. So if you suppose I'm looking at it from above, and this is my x1 and this is my x2, and this curve in 2 dimension will start looking something like this. Do you agree? I'm looking at this function from above.
Okay.
So, so say let me say this is your center, this is the center. Okay, let me draw it properly. So something like this. This is your x1, this is your x2. Suppose this is my center, say x naught, and x naught is, say, x1. I'm just naming terms here. Suppose these are the terms that I have. So in x1, x2, I have this point x1 0 and x2 0. Now I am looking at a radius of, say, suppose I say I'm looking at a radius of r1 in this direction. So what I will do is I will have a ball at a radius of, I have a circular thing like this at a radius of r1. Are you able to relate this and this?
Yes. It is like a contour plot, right?
Yeah, exactly. And this is a contour plot. So if I keep on increasing this radius, suppose I will get more circles like this. So this is at some distance of r2, and this will be at some distance of r3, and so on. So what the Hessian tells us is how much distorted this contour plot is. So suppose my Hessian is something like this, where my this, suppose this is 5 and this is 5, and these two things are 0, let's say. So it means that on the x-axis my radius, or the, so this generally says how much spread my contour plot is. So this is 5 and this is 5, that means our contour plot is circular. So if I have a Hessian something like this, say 10, 0, 0, and 1, so that means my contour plot is just bit skewed on one axis. So it will be like, so it is 10 on this side and 1 on this side. You'll get something like an elliptical contour curves, something like this. So Hessian basically tells us what is the curvature of our loss function that we have. So that is this thing about Hessian. Is this clear?
Okay, okay. Absolutely. Thank you so
Okay.
much.
So yeah, so the next question was to explain gradient descent. Okay, so now let us look at the function that we have. So we have some function, or if we look, if we write it down in the language of the course that you're having. So we want to have the loss. Suppose I say that my W has both the weight term and the bias term. I'm assuming that the this W contains both the weight and the bias variables. So our loss, I want to look at the loss. So what are you trying to minimize? We have some parameters, we enter W, and we want to minimize the loss. So this is the loss that we have, and we want to minimize this loss, right? So our loss may be something like this, and suppose I want to come to this point, from, say, I start at W naught at here, and from here I want to come to, say, W star. So what will I do? So first of all, I will look at the neighborhood of W naught. So what I will do is I will approximate this loss function around W naught. So as we saw here, we can approximate the function f around the point x1. So here I will approximate this loss function around W naught. So I will say log W naught plus h is equal to L of W naught plus some. We also add some eta term, but let me say I also have some eta term. So eta will just say how much further will I want to. Do I want to go this far? Do you want to go this far? So eta will control that thing. So we have something called eta. We will have h, and we have some gradient of L of W naught. And then if you look at the second degree term, we'll have n of eta of eta square. I'm not sure about this. So eta square by 2 factorial, the Hessian of loss, and so on. So since I'm talking about gradient descent, I don't need to look at this term. I don't want to look at this term because in general the learning rate is very small. Say suppose eta is 0.01, so our eta square will be 0.0001, which is very small. So we don't want to consider the larger terms. So let us focus on only the first term here. Okay, so we have L of W naught plus H is approximately equal to L of W naught plus eta times H. Or since we have a one-dimensional loss, I'm just writing this H. Otherwise, there will be some H transpose. So we have this thing. So now, if you look at this point, I'm looking at the function L around W. I'm looking at this region, say. And I want to know, because why do we want to do gradient descent? We want to do gradient descent because we want to minimize the loss, right? So if I look at the neighborhood of W naught in L, I want to look into the direction where your this loss will be minimized. So what I want is that L naught of W naught plus H, L of W naught plus H should be less than or equal to L of W naught, right? Now, what is L of W naught plus H? So this is L of W naught plus eta times H, gradient of L at W naught is less than this quantity. So we can cancel this term because these are positive terms, and now we can say that we have this quantity. So this should be less than 0, right? Now in general, what we do is we always say that eta is positive. We always say that eta is positive, and then we are left with this quantity. Now, so if we are looking into vectors, we can say that this lies between some quantities, say -1 and 1. But in this case, if you want this is positive, if you want this to be negative, right, we want this part to be negative, so it should be less than 0. So how can it be less than 0? Suppose our gradient, our derivative at this point is positive. Say our derivative at this point is in this direction. So I want to move in the opposite direction, right? Because I want to go in this direction. I want to move in the direction opposite to the gradient. So we take the direction of the negative gradient. So that means if we take the direction of negative gradient, so our L naught becomes L at W naught minus eta times H into L of W naught. So this is nothing but the update of this is the update step of the gradient descent. So is this much clear how we got to the update step of the gradient descent?
Sure, it works.
Sure. And so because we have to learn the weights, so how do we learn the weights? First of all, we'll go from W naught to say W1. After this, again, we'll do a gradient descent at this point and we'll move in this direction. Then we'll go to W2, W3, and so on. We'll go on moving until we come to this point, say W star. So that is why we run the gradient descent algorithm multiple times until we are satisfied with the results. That either we go to W star or we get the loss to be zero or some convergence criterion is uh, met. Okay, so am I not audible? Someone is saying the sound is not coming.
Yes, you weren't audible, sir.
Okay. So is my voice clearer now?
Oh yes, now it's clear.
Okay. So Raj, do you need me to repeat something about if you missed it? Let me. So are there any doubts regarding the this universal approximation theorem or the tower functions that were taught in the class? So we can go through that later if you need some clarity.
Sir, today only doubt solving will be there, right?
Yes, yes.
Okay.
So we can discuss the solutions from next session, but because the deadline is tomorrow, I cannot do this today.
Okay.
If you have any doubts from the last or the first week of lecture, we can also go through that if there's anything there.
Sir, one more point I got. I was just going through everything. One thing I wanted to make sure was, is dot
Yes,
product equivalent to inner product?
yes, yes. Dot product and inner product are the same thing, right?
And what is outer product? Then I didn't understand.
So outer product is basically, so okay, let me give you an example. So if you have two vectors, say 1, 2, and 3, and you have a vector say 4, 5, 6. Suppose this is your vector x, this is your y. So your dot product is basically your x transpose. This is your dot product. This is your x transpose y. So it's basically sum up, multiply and sum up. So this is your 1, 2, 3, and this is your 4, 5, 6. So when you're talking about outer product, your outer product is basically your xy transpose. So you have, so suppose, yeah. So you have your
So the
x.
answer will be same, right, for both of them?
No, 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 no. So this is your dot product. Sorry, this is your outer product. So for dot product, you have, so actually, yeah, I made a mistake. This is a column vector actually, because in we usually write these as column vector. So this is your x and this is your y. So dot product is defined as x transpose y and outer product is defined as x y transpose. So what will be the size of this?
3 cross 1.
Yeah, no, this will be a matrix, right? So because we have a 3 cross 1 and we have a 1 cross 3, so you will get a 3 cross 3 matrix here. So dot product and outer products are two different things. So for vectors, you get a scalar value for dot products. If you have two vectors, your inner product or dot product will be a scalar. For an outer product, you will get a matrix, say n by n matrix from the outer products.
Okay, got it, sir.
So if you're implementing this in NumPy in Python, so Python, if you're doing matrix products, so there are these type of quantities you must have seen this and then np dot dot. So you have to be careful that you do not have a mismatch of the dimension. So because that can cause issue uh, further down the line.
Okay, sir. Okay, so with this we can conclude that matrix multiplication is not commutative, right?
No, 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 it did not.
Like a matrix A into matrix B is not
Hmm.
equal to matrix B into matrix A, right?
No, no, because your this thing will change. So you're multiplying a row with a column, and but if you go to the other side, you'll make multiplying a different row with a different column. So those need not be the same.
And if they are of the same direction
Yeah,
dimension,
they will
then
have to be of the same dimensions, right? Correct.
okay. So, sir, when will we having the next session on problem solving?
So yeah, so there are regular sessions on I think Saturday, Monday, and Tuesday. So again on
Okay.
next, on Saturday there will be another TA. On Monday there will be another TA, and next Tuesday I will be taking the session.
Okay, okay. Okay, sir. Sir, so I'll leave now because I mean I've gone
Yeah.
through the thing and everything is pretty clear. Thank you so
Okay.
much, sir.
Sure, sir. Thank you. Hello, Raj. Are you able to listen now? So, okay. Yeah. So, if you have any questions, we can discuss it. So has anyone tried implementing gradient descent in Python? Uh, so you must be knowing Python, right? Uh, because that is very easy for implementing these deep learning algorithms. Has anyone tried using Python for implementing gradient descent? Yes, no.